We have been going down a little bit fairly. Started off so well.
That's not because they won't change this for that.
I look at the name of my book and well, I can find the names, but I don't know who they are.
And now the challenge is
To find out who our group is.
and for how long?
Yeah, I think we've got about 4 weeks.
And now that's a challenge, coordination.
Yeah, exactly. So we need to find out who our team is and well, this afternoon we'll talk to whoever. Yeah, we'll talk to them this afternoon. Yeah, so that means we're limited to evenings or weekends. Saturday and Sunday I work until 5 or 10 to 4. I'll 10 to 4. Whereabouts is it? Monday, Tuesday, Wednesday, we normally do about an hour. He comes about 5 times. But he's a lazy fucker. That's why he's going to be by the He's not a lazy fucker. Crazy. I tell him, use your pen. No, you're so lazy. It's good. But since Wednesday night, well, whereabouts is it? How much is it? Is it fresh? What time do we get home? Dropping me home for people. What the fuck? I like this already. It takes you home. This is perfect. Look. I might not even come, I might just get on the bus and sit me up. How long is it on for?
一直都有啊。
Yeah.
我要真在我抠呢。
Basically, about half.
Right, sorry, I was just struggling with the photocopy machine to take copies of your handouts. So please pass it. Okay, last time we started with the information that I'm giving you in the handout. So we have looked at incompressible fluids, and then we started looking at compressible fluids. And then if you remember, we're right now looking at solutions that take into account the non-ideality of the gas. And therefore, the way to solve them is normally through a software or a numerical method, right? So we started with an example last Wednesday, and today we're going to look at another example of how to estimate or the pressure changes in a pipe that has basically a flow, a compressible fluid going through it, and it's adiabatic. Okay, so what does adiabatic mean? Not heat transfer, and normally what type of pipeline will have an adiabatic flow? What would you look at in the pipeline? Insulation, no? So normally it will have a very good insulation, and therefore no heat exchange with the environment. So what will be the variable changing in this fluid? Throughout the pipeline, the fluid going, what are the variables changing in the fluid? Pressure, yes, and what else? Yes, velocity is kind of, will change. Well, you could maintain a constant velocity and still decrease the pressure, in fact. So it's not mandatory for the velocity to be changed. Okay, so what else? Pressure. Sorry? The volume, which is related to, for a compressible fluid, to density, and density is related to, what makes the density change in a compressible fluid? Temperature. Okay? So adiabatic flow will have no heat exchange, therefore Q remains constant, or Q is 0, but the temperature changes, right, throughout that, affecting the density and the volume of the fluid, and therefore affecting the pressure changes as well. So we have a set of variables that we basically need to right now estimate, which makes our mechanical energy balance quite complex. And in this case, one way to solve the mechanical energy balance, so the mechanical energy balance will normally have as a variable pressure, temperature, volume, and you will normally relate these variables through using the equation of state, right? So the equation of state relates PV equals nRT, relates temperature with pressure and volume. So we normally use an equation of state in order to be able to simplify one of the variables and perhaps take out density and relate density to pressure, for example. So one of the equations of state that is used for, in this case, we're going to use a cubic equation of state, which is a way to basically relate pressure, volume, and temperature together, but taking into account the non-ideality of the gas. Okay? And for example, we have the Rendlich-Form equation of state. And like that, we have a series of equations of state that can relate these variables using the non-ideality of the gas. And why do we need this kind of equation of states, which are a little bit more complex, because there are several gases that behave as non-ideal, and especially when we have very high pressures. So when we have pressures higher than 5 bars, it would be off the trend to assume that that gas is a compressible flow, but it behaves as an ideal gas. You have to take into account the non-ideality of the gas and therefore use a more complex correlation between these three factors. So we will look at the same pipeline that we saw in the previous lecture, this basically system, but now we will assume adiabatic behavior, and we will use the cubic equation of state instead of the ideal gas law in order to approximate this relationship. Again, these kind of calculations, basically what you have to do normally when you have a complex problem like that is look at that, define which is the equation of state that you are going to use, define some initial inlet parameters, input that into a software modeling, and get the result. Okay? So normally this type of softwares will not solve it if you don't give the right initial conditions and select the right equation of state, in order to be sure that you are getting a realistic solution. So again, going back to the three equations, the differential equations that are used for compressible or incompressible flows, in this case, to specify the mass balance, momentum balance, and use them in order to obtain the energy balance. Okay? So the way the pressure changes with distance can be related to density and temperature changes using the equation of state, something that I've already mentioned. And in this case, we're going to use a cubic equation of state. Why? Because these are the most common used, but they can be other types of approximations. So a cubic equation of state is used in order to account for fluids going to higher than 500 kilopascals. So when you have pressures higher than that, you cannot use the approximation of ideality. Why? Because above this pressure there are attractive forces between gas molecules that invalidate the assumptions underlying the ideal gas law. Okay, so if you remember when we say which assumptions were, we said that in an ideal gas law we were saying that molecules are so far apart that they don't interact. But if you have very high pressures, then you are sort of compressing the gas very close together. So now you have some interactions in the molecules with some activity coefficients given because of these interactions that you need to take into account. And that's basically what the equation does, which becomes a little bit more complex. So the ideal gas law predicts that at infinity pressure the volume of gas will be 0. This is not the case, so we introduce a minimum volume. Okay, so in here, basically, we will denote that as B. And we basically use the interaction forces, which will be A in this case, are inversely proportional to the volume square. Okay. So the initial equation of the van der Waals equation to suggest this modification becomes the one that is denoted here, where we basically have the volume versus the minimum volume minus the minimum volume, and the activity coefficient divided by the square of the molar volume. So A and B will be constant, and normally this can be found if the critical temperature and pressure are known. So normally the software package sometimes will give you these constants once you define the type of component that you're working with. So a cubic equation of state predicts both the liquid volume and the vapor gas volume. So again, now we need to account two changes in volume because of this compressibility that at very high pressures needs to be taken into account. So basically here what you need to look at is how the equation of state now has increased its complexity, right? And how we are taking into account now other changes into the system. So in this case we have basically the approximations using what we're basically using different variables in this case, and these two equations are also known as the Penck-Robinson equation. The last one, the Penck-Robinson equation, which is another equation that also approximates sort of the relationship between pressure, volume, temperature, and density changes. So let's take an example. If we have a mixture, for example, of 80%, 10% of ethane, and 10% propane, this will be sort of the activity coefficient and the volume, the minimum volume defined for this property, and this will be the molar, the moles going into that. So how many solutions will an equation of state have? Do you know? How many solutions will give an equation of state?
As many as the order of the equation.
Okay, so as many, so how many? Three. We will have 3 solutions in the equation of state. Okay? So in this case, in the cubic equation of state. So in this case, for example, we have the approximations that were done to solve a problem with the specifications that were denoted before, and this is just to let you know what are going to be the 3 solutions that you can observe. So a cubic equation of state, we generate a curve, and normally you will have 3 points where you will have the solutions. So normally the lowest value in this case will correspond to the value of the vapor density, and the highest value will correspond normally to the liquid density of the system. Okay? If we go to pressures above the critical point of the system, then we will in fact get 3 answers, but 2 of them will be imaginary. So above the critical point we actually get only 1 answer, which is correct, okay, which will be a real answer in the system. Right, so over here this will be the isotherms at constant temperature, so we can see the different temperatures and the isotherms. basically, and how the system is solved. Now, why we need to account and use a cubic equation of state? And this is basically a chart to show you what is the changes within a system that is ideal. So this will be the density calculated using the ideal gas law approximation, PV equals LRT. And this is the density calculation using the Rankine-Knowles equation, the Redlich-Known equation. So we can see how this approximation deviates from 1, okay? So as we increase the pressure, the deviation becomes higher and higher. So if you were to use the ideal gas law at this pressure and the Redlich-Known equation, you will get 1 in both cases in terms of calculating the density changes through the system. So that means that the ratio between one and the other, you get basically the same answer. Can you see? So you get the same answer. But as you increase the pressure, then the answer with the non-ideal gas law will deviate from the ideal gas law. And it deviates, well, let's say this is more or less 5% in this case. So that's why we need to take into account the non-ideality of the system at higher pressures. So by substituting everything into the equations that we saw at the beginning, mass balances, momentum, and energy balances, and using the Redlich-Known equation, we get this type of approximation. Okay, so which basically tells you the differential of the changes of pressure through the distance will be related to the changes of temperature through the distance and the changes in density through the distance as well. Right, so normally in order to make this system a little bit easier to solve, we can define these two variables, kappa 1 and kappa 2, and basically define our equation as the changes in pressure over the length of the pipe will be kappa 1, the differential of T over dx, and kappa 2, the differential of. So basically we're substituting these very large equations by these variables in order to make an easier expression. So substituting the pressure gradient in the mass, momentum, and energy balances, we basically get these equations with the kappa in here, and that will be the system that will need to be solved basically for the pipeline. So we will look at the changes of density through the length of the pipeline, the changes of volume through the length of the pipeline, the changes of temperatures through the length of the pipeline, and the changes of pressure that was in the previous equation. So the model will basically give us these results where we have a chart which tells you the changes throughout the length of the pipeline. So here we have the changes in density through the length of the pipeline, changes in temperature through the length of the pipeline, pressure, and changes in volume, which basically you can now look at these equations, these relationships, and look whether they make sense or not. Okay, so as the fluid goes through the pipeline, is it right that the pressure is going down? Will it be coherent? And so why the volume is going up? Okay, so the gas is expanding because it's losing the pressure. Now, why the temperature decreases as it goes through the pipeline?
Compaction. The density of the gas reduces.
Because of the surrounding
No, this is adiabatic, an adiabatic system.
2000.
So where is the system getting the pressure from? The energy, where is it coming? We said that we could get the energy from the internal energy. And normally if you get the energy from internal energy, the fluid will decrease in its temperature. So since it's not getting energy from the surroundings or from a compressor, it's getting energy from its own system using the internal energy that is in the fluid. Therefore, the temperature is increasing while it goes through the pipeline. Is that clear? And then why the density is decreasing?
Can you repeat the part?
Of the temperature?
Yeah.
So in this case, we have an insulated pipeline. Okay? So basically, as we decrease the pressure, you are using certain energy for the system to flow. Where is the energy coming from? Where is it if it's an insulated pipeline? Internal energy. And the internal energy, as it is used, it cools down the fluid. It's more or less the same thing as expansion. When we do an expansion, we cool down the fluid, right? So here we are doing an expansion process by decreasing that, and we are cooling down the fluid. Is that clear? And the density decreases. Why? Why is the density decreasing? Because it's expanding, no? So as it expands, it's less dense. So basically, when you get these sort of results from the modeling software, you need to check that they make sense and that everything has been run correctly. Right? The software will not give you the right answers. You need to check that they are right. Okay? So here we have a comparison between the ideal gas and the cubic equation of state. And basically, these will be the conditions. So in the cubic equation of state, it will tell you that if you remember the problem that we had before, we needed the inlet pressure. What was the pressure in order to solve this? And here we solve it as the ideal gas law, and now we are solving it as the cubic equation of state. And we can immediately say that the cubic equation of state is telling you that you will require a higher pressure. So if you were to use the ideal gas law and buy a compressor, then perhaps your compressor will not achieve the pressures that you require to deliver it at the conditions that you want. So the cubic equation of state in this case will be a better approximation and will give you the right work that you need. Now the density of the outlet, the velocity of the outlet, and the temperatures of the outlet also changed between the cubic equation of state and the ideal gas law. So the majority of the differences will come from the inlet pressure, so in this case it will be 20% higher, and the outlet temperature, which will be lower in this case. Okay? So, and you can see that that makes sense because the cubic equation of state is actually given a better approximation of the internal energy that is being used. So therefore the cubic equation of state is telling you, well, actually more internal energy is being used in the system. Therefore the temperature at the outlet will be lower. You will have more energy losses on the system because of this expansion.
So this comparison is to say that the outlet pressure is the same. How about you
No,
comparing
you
it?
remember that if you remember the last problem, the one that we solved on Wednesday, it's a So in here, we actually wanted to deliver at atmospheric pressure. And we wanted to know the pressure at the inlet that we needed to go through the whole system and deliver at atmospheric pressure. Right? So last time on Wednesday, we approximated it using the ideal gas law. And this time we're approximated it using the cubic equation of states. Right? And we're looking at the differences that a cubic equation of state or an ideal gas law approximation will give you. So the most important thing as engineers is actually selecting the right equation of state that you are going to use for the system. And in this module, we're just going to look at these two equations of state, but there are thousands of equations of states depending on the fluids that you are working on, pressures that you are working on. And when we go to the HYSYS software, you will see there's a list of the equation of states, and you only have to select the one that you want to use. So, okay. So that's basically how we use modeling software in order to solve compressible fluids. When we have, let's say, when we take into account the changes in volume. Now, there are two ways to simplify these compressible fluids in order to give an analytical solution. And here we have what we call the isothermal flow. So what we do is that in isothermal flow, basically we have a constant temperature, so therefore the temperature doesn't change throughout the length of the pipe. All that derivative or all that differential equation will be constant, and then it will simplify the solution, and we will end up with this equation. Now, I didn't bring, I'm not sure if at the end of your handouts, is there like something that says support or something like that, or not? Yes or no? I don't know. I'm not sure if I attached it. Yes, the supporting information.
Where is it?
Here. So, at the end of your handouts, the three last pages is supporting information.
Regarding question about this big equation in ideal gas law, why is it a big high difference for the inlet pressure?
Why does it have a high difference between the ideal gas law and the cubic equation of state?
Yeah, because it's asynchronous.
Because how you calculate the changes of density.
About 10 bar difference?
Above 5 bar pressures, it's more accurate to use a cubic equation of state, because the cubic equation of state takes into account the forces between molecules. At a high pressures, there are more interactions between the molecules. So that's why there is a difference on that. But for low pressures, then you're able to use the ideal gas law. Are there any spare handouts? Because I don't.
Yeah.
So you have your handout in there, and then basically we have in here, if you remember, this is the general energy balance, right? So internal energy, kinetic energy, pressure energy, potential energy equals friction through the pipeline plus a heat flow in there, right? So basically this, if we do this assumption, so given the low density of gases and vapors, we can ignore the potential energy term. Okay, so we take out the potential energy term because of the very low density. So there's no a big difference on that part. And then basically dividing the total energy balance by the density and volume and replacing by the friction factor, we get the form to use this equation that is here. Now let's go to the isothermal flow. In the isothermal flow, basically, what will be an example of isothermal flow? So for example, here we have a reservoir and a receiver. We have a fluid going through the pipeline and we have a heating jacket. So we maintain the temperature of the system constant through the heating jacket that is here. Okay? So in this case, if the temperature is constant, therefore the thermal energy of the fluid will not change. And then really I won't get into, not the purpose of this course to go through the whole mathematical procedure, but you can read that yourself. I think the most important thing in here is the definition of the mass flux, which is, if you remember when we started with compressive fluid, we said that the density and the volume changes, but because one is inversely proportional to the other, the multiplication of the two is constant, basically. And then we define the G term, which is mass flux, which is a constant variable. And it's very useful to have this one because then it becomes a constant variable in the system. So we substitute basically the G value throughout the equations. We perform the integration, and then what are we using to integrate this equation? What is this? The ideal gas law, no? So we are using ideal gas law to as the property in this case. And then through the integration of the equation, we get this large equation, which is for an isothermal flow. And this is the equation that we use in order to solve analytically an isothermal flow going through a pipeline. Okay, so let's say we wanted the pressure at the outlet. Here we'll basically have we'll be able to take it out from the equation. So this equation accounts for the reversibility of the due to pipe friction, and it assumes that the gas expansion process is reversible when it's not. This equation is applicable over uninsulated pipe lengths of less than 5 kilometers and pressures where ideal gas law applies. Okay? So when we have a pipeline that is very short, we can assume that the temperature changes throughout the pipeline will be constant when it's very short. And this is how this equation that is presented here is obtained. Okay, you don't have to learn this derivation or anything. It's only for you to understand. Okay, those derivations will not be asked in the exam at all. So, just for you to know how these equations are basically obtained. And then again, here we have the same system.
Excuse me. The last part. It's 4F.
Well, again, we're not defining the friction factor. So it will depend whether you are using the Darcy friction factor or the fanning friction factor. So I think that for the handout fanning friction factor and perhaps there is Darcy friction factor, right? So yes, so perhaps it will be useful to define it. So that doesn't. Any other question? So again, for adiabatic flow, we do the same. Okay. So you have here in page 4 of the supporting information. Again, all the derivations and how we integrate and get into the final equation. I think here the most important part is the gamma that is basically defined into the equation in order to allow us a better approximation on the adiabatic flow, which is the ratio of the specific heat capacities for a gas. So these equations have been assumed that the pipe is horizontal, although in reality changes in elevation between one end of the pipe and another do not have a large effect. So again, because it's a compressible fluid and we're assuming that the density is very large, then it won't have a very high effect. So what will be the limitations of this system? These systems are used for pipes that where you have a fluid going at low pressures. Normally when there are short pipes, they're not very long pipes. And also if you want a quick approximation and you don't have any kind of software such as HISIS, anything, so you just yourself, then you will analytically solve this through the system.
Excuse me. Did you say when the density of the fluid is high, then that changes elevation? Or it's not?
When the
density of the fluid, when it's high or when it's low? When does it have an effect?
sorry, when the density is low. When the density is low and then it's expanding. Therefore, it won't have a lot of changes in the potential energy of the system. Yes, and it's the other way. So if we say write down the main cases used to simplify the solutions of an energy balance for compressible fluids, which are the main cases that we saw? It's a very easy question, actually. Yes, insulated pipes, short pipes, so adiabatic flow or isothermal flow. Okay, so these are the two cases. And what are the main equations used for adiabatic and isothermal flow? This will be for adiabatic flow and the other one for isothermal flow. So let's have a look right now at an example. Okay, so you have an example there. In the case of the analytical solution. So in this case you have an example where you need to determine the isothermal and adiabatic flow. So compressed air at 450,000 pascals flows down a steel pipe 35 millimeters in diameter and 200 meters long. The pipe run has 28 standard ratios, 20 bends, 90-degree bends. The absolute roughness of the pipe is 0.045 millimeters.
Where's this example?
You don't have it in there? Sorry, I think it printed incorrectly. So the temperature of the pipe inlet is 305 kelvins and the mass flow of the gas through the pipe is 0.06 kilograms per second. For air, the gamma, which is the ratio of the heat capacities, is 1.41 and the viscosity is as shown. Calculate the pressure at the end of the pipe, assuming the flow is isothermal and assuming the flow is adiabatic. So the first thing we're going to do is basically look and obtain the variables that we need for the equation. So we obtain the cross-sectional area of the pipe, and then with this cross-sectional area and the mass, we get basically the mass flux, G. With the G, we are able to determine a Reynolds number. And with this Reynolds number and the relative roughness, we basically obtain the friction factor of the chart, of the system. We were given bends, 28 bends, and the LD equivalent for one bend is 34.4. So for 28 bends, it will be 963. The LD of the pipe is 200 over the diameter of the pipe, and that will be the LD of the pipe. So here we have input everything in Excel. So we have the diameter, the area, mass flow, G, mu, Reynolds, rugosity, friction factor, LD of the pipe, LD of the fittings. We have the initial pressure, temperature, and the mass flow. So now we can basically input that into the equation and solve for pressure 2 until this equation gives us 0. Okay? So basically the way it's solved is that we start guessing different values of pressure, and then we get more or less negatives in here. We get positive in this case, so the value is between 300,000 and 400,000. So we obtain this value and we basically get 0 around there. Okay. So that was basically obtained through the solver function in Excel. Do you know how to use the solver function in Excel? Or not? No? I'll show you in a second. Which is basically helps you to do the iterations, right? You can guess there and have the ranging here, but solver will be a function in Excel that you input the equation, you say that you want it equal to 0, and it will basically tell you which is the parameter that is there. Right, so we'll take a break right now of 10 minutes, and then we'll look at the adiabatic flow, and after that I'll give the assignment as well. So. Yes. This one? Momentum balances. Momentum balances. Yes. I think it's fluid flow supporting handles. I put it in the. I think I have some. I put it in Blackboard. Right? Put this one and the other one.
Because we are seeing them.
Let me see what I have in here.
Not everyone.
You're gonna see it in the last one. Oh, well, I just have that in there. So. I'll just take this one. Yeah, that's fine. Don't worry. Okay, I'll come in a second.
Now we need. So we have to have at least it's someone. I didn't. I looked at them. Oh, that's good. There was got that in a car. Because it's actual name, I have no clue.
We have the mass flow. We know the mass flow. But this is
So okay, so we've got that one. What's that? This is 4.
I'll take out the Excel file. I'm just going to pick up some
专门讲就是这边贴审核的工作。普通话什么我不知道，是教英文的话我不知道。
他是教语言培训的，然后有一个是组织培训，然后最后他有错了，
他都是你看都是关于这个关于。
教育机构都是受过。教学的是不非常来管理岗位。
因为我看这个我们同学会的
那在一起是。Is it?
你们找美国人。
I said the guy who got 70-something%. Yeah, but I'm assuming you've got a distinction. So, I don't know. How much is your that made me cry. And I run outside shape.
为什么我打清楚出现的私密处？
Because that's normally what comes up with it.
你看，我打清楚，刚刚第一个私密处是第一个。
This is 20% wrong. They're all 20%. Have you all 20%? I noticed that I asked it this mistake. What I got masters last year, like in bachelor's, like only your top only your top 5 marks. Why is that percentage? It's fundamental.
式分工方教导课程，注意产业和流程投资吗？ 董事长忠诚的吧。也不认识。你不给我钱，给我钱我才在那里问。经理在前面。如果他这个人就是你。这应该是我爸爸。叫啥呀？这门故事挺深的。
Oh, the big M is the molecular weight of compressed air. Air.
Molecular weight.
Air. It will be taking oxygen and nitrogen, 72% nitrogen, 20% oxygen, and then it will give you more or less this 284 grams per mole. 28.4. Oxygen is 16. Nitrogen. So that's basically the molecular weight of air. So please, if I think Thursday, yes, it was a heavy set of lectures because they were all together. But unfortunately, that's the only way we can have somebody from industry coming because they're basically unable to come on a weekly basis all the time. So I hope that it was worthwhile, even though it was so fast. And we're going to have questions for his part for the exam as well. So they're not going to be problem-based, but there will be questions on this part. So the handouts are in Blackboard. So I think that it will be good for you to start revising them. And if you have questions that weren't clear because everything was so fast, send them to Nigel and copy me, and he will be able to be in touch. So he has offered him to be in touch through email before your exam, so take advantage of that. And also if you want other questions which are more related to how to apply these systems in the real work life, I think that just take this opportunity right now that he has offered his support to just email him certain questions, and don't wait until the exam season because then everybody does that and then it's impossible to answer. So just do it right now that you still have the ideas fresh. And
Upload the past papers.
oh yes, I upload them. So don't worry about that. I think that what you have to worry is about finishing the tutorial problems that we have in Blackboard. So we have the problems 14, 15, which relates to liquid flows in pipelines, which was what we saw 2 weeks ago, and 16 and 17, which relates to compressible flows in pipelines. Okay, so I think that it will be a good idea now, this weekend or anything, to start working on this, because next Monday we'll start looking basically at dew point control and distillation, which is a completely another subject. So if you are clear on this, then we'll move on. Okay. Okay, then, so here we have the example. For the isothermal process, okay? You have all this information in Blackboard, so you're able to download these files. So here we have the equation for the isothermal process and all the variables that basically we need in that. So M is the molecular weight of the solution, and in this case that will be the molecular weight of the air that was specified as the type of gas flowing through the pipe. So in here I've put all the equation basically using all these variables in here, right? Can you see that? And then I need the solver. So don't remember a lot, but let me see if I go to that. Okay, so I go to properties, add-ins, and in add-ins there's something that is called solver add-in in Excel. So I select that. Okay. Is it showing now? Or? I'm not sure how to. Okay, so you have to click on here, solver add-in, and okay. Add-ins. Oh, it's not here. Where is the solver function? So it seems that it puts it in data, under data, and then you go to solver. Okay, so you click on solver, and you have here solver parameters. So all my equation, all this equation is in here, right? On this cell. That is over here. So I've selected C21, and I want all this equation to converge to the value of 0, right? And then what is the changing variable that I want? So all this equation as well, I've input pressure to this cell, and then I select that I want the solver function to make converge this equation to 0 by changing the pressure variable in this case. Okay, so by changing variable cells pressure. And then I can make some constraints. So I can say this pressure should be equal to or 0. So it should be higher than 0, right? So it doesn't converge in negative values. So I can select the solving method, but I will just use that, and then I click solve. And then it has converged this equation to 0 by changing this pressure too. So how much do you get in the handout time? So 387,963, 397,433. So it's an error given by the calculation, I suppose.
Why you change the friction?
The friction, no, it's the same one. So that will be the, let's see if I input this. So no,
Minus.
yes. So that will be the value. So the actual value that is here is not correct. It won't converge at that value. Okay, so change it to the 397,433.8. Okay, Pascals. I'll come back to the this value because I think that with my writing. Right? Is that clear how I selected the solver function and how I made it work, or do you want me to repeat it? Repeat? Okay. So should I go File? Then I go into Options, okay? And then I select Add-ins, right? In Add-ins, I think that we need to go to Excel Add-ins. And then we can have these add-ins. Euro currency tools, analysis toolbox. So we'll select solver add-in. And we click on OK. Okay? So when we click in OK in the solver add-in, that will appear in the data toolbar. Right? So now what I need to do is that I've typed in my equation inside this cell. So if we look at this equation here, and this equation here, so it's G squared, where is G? CH squared natural logarithm of pressure 1 over pressure 2. Pressure 1 over pressure 2. Plus M, which is molar weight, pressure 2 square minus pressure 1 square. Pressure 2 square minus pressure 1 square. Oh, yes?
Pressure 2 is not given, so but I was supposed to
Yes. Pressure 2 is not given, but then this, let's say, is not given. Okay. I'll get div 0 because it's impossible, so I'll just, for the sake of not getting that. So pressure 2 is not given, but I still need to put a cell because that's the variable that I want to find out, basically.
Say O should be 0 equal to 0.
Yes, but I don't write here equal to 0. So
Yeah,
all should
no,
be
I mean
equal to
so.
0.
Alright. Okay.
That's why the equation is equal to 0, right? So here we have pressure 2 square minus pressure 1 square over 2 RT plus 2F LD G square, right? So I've input all the equation here. Now I go into solver here. I click that and I select the equation that I want to work to converge to 0. So the equation is Basically, this could be, I could select anything that I want, but I'll select where I have input the equation that I want to convert to 0. C21, at what value I wish this conversion to be equal to? Value of 0. I could here say 20 if I wanted it to make another value or if the equation was different. What is the variable that I'm going to change in order to make this equation convert to 0? The pressure at the outlet, pressure 2. So I select C24. So I can add constraints. These constraints help. This is basically an iteration tool. And the constraints helps for the iteration to follow the right way or the right pathway. It's just some guidelines. So I just say the pressure cannot be negative, the pressure 2. Okay, so it has to be positive. So it doesn't converge at a 0, giving me a negative pressure, which actually will be unrealistic but mathematically possible. So once I get all that, I just click solve.
But the question is why it's not equal to 0 then?
Huh?
At the end, why it's not equal to 0?
Where? So here, you mean?
Yeah.
Well, the first time I converged it, if you remember, it gave me minus 1.2 10 times 10 to the minus 7. So that will be 0.00000000.
Yeah, I know, but
So it does converge to 0. Now, it will depend a lot on the initial values. Now, you have seen that I've given an initial value of 100,000, I think. So this one is converged to 0.2. So it's not converging completely to 0. So it's asking me if I want this solution or if I just want to cancel it. So I can cancel it and then start with the 300.
we need to start with 300.
Well, the problem is that it doesn't matter when you start, but depending where you start is how the iteration is going to converge, basically. So if you remember last time, I started with 100,000 and it ended up in 0.2 instead of 0.00. So because it will need more iterations to actually get to that value, then it just stops there. So, well, now it's just converging.
Same key to different iteration.
It's a slight change, really, because it's 397,433.8. Well, really, in terms of engineering terms, decimals here, especially for pressure changes, we never report decimals. So we stick to round values, basically. So that's how this was solved through Solver. So you have all this in your Blackboard. So in Blackboard you should have the slides, the supporting information. This is something on pipe fittings on the K values. That's so you have here all the K and LD equivalents for fittings and valves as well.
Gate valve. Gate valve.
Yes, globe valve. Gate valve is here. So here it's very important that you look at these charts because the K value depends on the opening of the valve. Obviously, if the valve is less open, you have more friction, more changes in pressure than if the valve is more open. So actually, the K value changes according to the opening. Having the lowest K value at the highest opening and having the highest K value at the lowest opening. So you have that as well in Blackboard. The gas flow handout plus the supporting information and the examples of the gas flow that we are looking right now. Okay, so you can go again into Excel and try to the solver function just to see whether it works. So now let's have a look at the adiabatic solution of the pipe flow. So in this case, we have this equation that we need to solve numerically. And basically, the way we are going to solve it is that we will input again all the variables in the system. So diameter, area, mass flow, mass flux, viscosity, Reynolds, relative roughness, friction factor, LD of pipes, LD of fittings, R, ideal gas constant, pressure of inlet, temperature of inlet, molar weight. And in this case, we include the gamma, which is the ratio of the heat capacities at the density. In order to find the density, in this case, we use the ideal gas law. Okay? So in this case, we will have a set of equations for the temperature, for the pressure changes, and for the temperature changes, because the density is dependent on the temperature changes. Okay, so we'll need to look at the density, how it varies according to the temperature changes in the system.
So for the pressure change, are we doing the same thing that we've done before? Over it.
So again, here I assume several pressures, and this A, B, C is basically I'm given A, some of these constant values. Okay, A will be that value, B will be that value, and C will be that value. And basically I'm calculating the constants as A, B, C, and taking all with respect to the temperature. And then with that temperature, using the ideal gas law to obtain the density. And then I input the density in this equation and obtain the pressure at the outlet of the pipe. Okay, so I use as well the gold silk function and solve it. So adiabatic flow is a little bit more complex than isothermal flow, because we also have to take into account the changes in temperature and the density changes in temperature. Yeah, sorry?
No, first one, why it's not 0? Which one?
This is, well, it's 7.68 10 times to the minus 5.
The last one. Okay.
So this is exponential to the minus 5. So it's 0.407, which is kind of 0. We'll never give you 0 or 0, 0.
So you get for the pressure 2, you get 38, 69. This
Yes. So again, you can start doing it, let's say, by assuming some initial pressures. So, sorry, some exit pressures. And then at the end we get, through the solver function, the pressure that we actually need.
For the temperature, you just
The temperature was
Type
calculated through.
can't type it.
So took out temperature out of the equation. Right, so you can look at this through the blackboard again. And in the handout, in your tutorial, for compressible flows, you have an isothermally, so this will be an isothermal flow and an adiabatic flow. Okay, so just one example calculating it isothermically and another one adiabatically. So I suggest you do this week, and next week, if you had problems with that, we can go through that. Okay?
So 16, 17.
16 and 17 is compressible flows, so it will be this part. So I suggest you do these two, especially right now. And 14 and 15, they are non-compressible flows, so it's a little bit easier to obtain. Right?
Assignment.
Okay, so now we'll go to the assignment. So I'm not sure if I have enough. Okay, enough for everybody? Or? Okay, so the assignment to be submitted the 20th of May. So 19, sorry, 19.
Okay, 20th.
So, no, 20 is Saturday, so it will be difficult for you to submit it that day. So you have almost 2 months to do the assignment. So hopefully that will give you enough time to reason it and to submit it. Now, so what do we have for the assignment? So basically, this is a collection of the flow processes that we have seen throughout this module, right? I think the only part that is missing here is pipeline changes of pressure due to pipeline, which you don't require to calculate. So this is why you should finish the tutorials on compressible flow on that, because you won't rehearse those ones in here. So basically, you have this process flow sheet, and you will need to obtain all the components throughout the flow sheet, doing mass and energy balances on that, and give basically the temperature changes, pressure changes, and flow fractions around it. So we have a system which receives a feed of ethane and propane, a mixture of ethane and propane, and what we need to do is basically divide these two components into two flows, right? So we want to separate them. That's what we want from them. So we have a process to separate ethane and propane using distillation, as shown in figure 1. Right? So the only thing that we are still missing right now is to look at distillation, which will be the last part basically. And we'll start looking at it next week. In this process, a feed containing ethane and propane is compressed from 103 kilopascal to 850 kilopascal. So the first thing is compressor. After that, once this flow is compressed, what will happen to the temperature? If it starts 298, what will happen to the temperature here? It will increase, okay? So it has an increase in temperature, and then we have 3 pre-cooling stages, okay? So we cool down that flow to 3 stages.
Why 3? Remover is not cooling.
Yes, in this case it's cooling. It's a cooling stage.
But it should be the heat exchanger, not the remover.
Yes. Depending on the temperatures that you have in the distillation column with the temperatures of the system.
Because the remover is remover.
Yes, it's boiling. Whatever is heating up, whatever is in the distillation column, therefore taking out heat from the flow. Can you see that? So basically we have first of all the first heat exchanger. We cool this, which where we are basically, this will be a little bit of heat integration system that is used a lot in industries, where we use as many flows through the systems to cool down onto heat processes in order to avoid utilities here. So we have a pre-cooling stage where we cool down with the flows, flows coming out from the separation processes. And then we have a second cooler in here. Yes, we cool down using a flow, and we cool down to another temperature. And finally, the final stage of cooling down to 254 kelvins. Okay. So firstly, using ethane and propane product streams. Secondly, using refrigerated pre-cooler. And finally, by passing it through the reboiler of the distillation column. So now the compressed and cooled feed is depressurized through an expander. So we use a valve, a valve here to expand it again, which has an isentropic efficiency. So in this case, I think that I'm not sure if you need the isentropic efficiency. So just take out, please, isentropic efficiency from your handout. Okay, cross that part. So depressurized through an expander valve to 101.3 kilopascals.
Which one? Efficiency, you don't need it, yeah?
No, you don't need it there. So it's just the valve. You're not producing any work or any. Okay. So you go to 101.3 kilopascals and 200 kelvins. So it's further cooled down by this expansion. So after the valve, the vapor and liquid phases are in equilibrium. Okay. And they are separated in this. So we separate the vapor phase and the liquid phase in this case. The vapor from the separation.
Vapor, it's not vapor, I think it's liquid.
Huh?
The downside is liquid.
Yes.
And the vapor it's going up.
Yes.
Yeah, and going down, and it's going to outlet. Then from this one.
Then you have a further distillation.
Yeah, you have further distillation. Where you have the liquid part as a.
So here the propane is going through here. The propane and the not propane in this case will be the ethane. Mostly the ethane will go through here. And okay, yes, I think he went a little bit. So we have the valve, and then we have vapor liquid phases in equilibrium. Okay. So they are separated. The vapor goes through the outlet, and the liquid goes through a distillation system, right? So the distillation system will basically further separate to get you a higher fraction of of propane in this case, a higher fraction of propane product in here, and whatever went as vapor, in this case the ethane, will go through the system in here, through the vapor. So this will be a vapor, that will be a vapor, and they will come together in this case.
How are we separating this? Are we heating up or it's by gravity?
In the distillation column? Through changes in boiling point. So yes, this part you still don't know how to calculate it, because that's what we are going to learn next week, the following weeks. So please don't get too confused on that, because you haven't learned how to obtain this part. But what you should be able to do now is compressor, heat exchanger, and expansion valve. Okay? So right now you should be able to get up to this point, actually, analytically. And then when we do the distillation columns on the next weeks, then you should be able to calculate this part of the solution.
If you put there a boiler, it means you should have temperature in your separation.
It's through the separation on a distillation column is through the differences in boiling point of the system.
Questionnaire. The system is.
Okay, when we look at distillation columns, then you'll be able to
So then,
know how
the
to.
page goes to repoller again, yeah?
Yes,
Then it goes there.
it goes out. So this temperature over here.
So it has to repoller again, yeah?
See, yes, so both before going out, they pass the press cooler. So that means that here they have a temperature. Will the temperature be higher or lower?
This?
This one.
Which
Will
one?
be higher. So you are delivering it at a higher temperature that you have it in here. Because you are using it to pre-cool that, so it's taking out the,
It's taken out
it's taking out heat.
from this one.
Yes, yes. So you are delivering at a higher temperature.
Most of them.
Yes, both of them. Yes. So, so here we have the propane and ethane product streams leave the pre-cooler one at the same temperature. So here they will have the same temperature. Same temperature. Over here. So they will have different temperatures here, but they will end up with the same one. So using the data provided, sorry, I put the dates. What is the data? Please correct that. Using the data provided and assuming that the liquid phase is incompressible and the gas vapor phase is an ideal gas. Okay, so we're making incompressible the liquid and the other one ideal gas to sort of simplify.
Sorry. Then question, are we going to model this one in HYSYS?
Yes, that's the,
So we don't need to do some calculations?
yes, you know, Judy.
We need to just
You need to compare your calculations with the HYSYS model.
That's why. So you should be correct.
Yes. So basically, all of you should end up with a correct solution.
Oh. 25.
Well, yes, if you do the model and then compare it. So find all the unknown mass flow rated compositions, pressure, and temperatures for the process streams in figure 1. Okay, so you want everything from the figure, the complete stages of what's happening in the process. Calculate the work required to compress the feed and the work out. So please take out the work gain in the expander. So cross that out. So just calculate the work required to compress the feed. Okay? In B. B,
Yeah.
1B, calculate the work required to compress the feed. Dot. Okay, so I've changed. Yes, so the expander is not applicable. We don't have an expander in this case. It's about. Okay. So calculate the number of stages required in the distillation column. So that's what you.
stages.
Yes, again, may seem a little bit confusing. In this case, a number of plates. But we will see how to model distillation columns.
Yeah, but so are we going to put the plates in this column?
In distillation column, yes, the distillation column normally has a series of plates.
Yeah, I know, but so are we going to calculate this?
Yes.
Okay.
And HYSYS also helps you to calculate number of plates, and you'll do it manually as well. Model the process using HYSYS simulation software and compare the simulation results with those from part 1. Okay? So, basically, you need to submit a soft copy online and a hard copy.
Soft copy of
So basically, you'll need to put your equations, type them in. All your equations need to be typed because Turnitin will check against plagiarism. Okay, and we don't have them typed, then we cannot check against plagiarism. Then we'll have.
So, it's not going to be the same problem as quite a lot of mathematical functions where we use the right
Yeah.
formula to have a massive similarity.
Yes, it is. Well, at the end, I think that it will be sort of the workout and the approachability. Basically, we just need to have them because of official regulations. That's not because of this. Sorry. Without soft copy? Well, in the chemical engineering school, we have that. But if you have any comments against that, then you'll need to approach the head of school, I suppose.
Can I submit an Excel sheet? Use calculation.
The problem with that is that it's difficult to actually run it through 13, through the Excel calculations.
If we have time in the equation is the same, so it will anyway show the budget.
Yes, yes, yes. I mean, but I think that it will be kind of the way you approach the solution, your own explanations. I mean, you don't have to show all the equations. I think that if you give the general equation that you get and the solution, then that should be all right. Okay, and you can put in appendix all the working outs. But basically you have to show that it has been produced by you. Okay, so the hard copy as well. And then obviously the HIC simulation through the software. Perhaps what you'll do is a printout of the flow sheet, the mass balances that you get through the variables that you get through the software, and a little bit of discussion of the comparison of one and the other. And that's it. So you have anyway, I think, enough time to sort of think about it and be able to type a little bit of these equations.
I guess we have a lot of stuff. Apart.
The life of a student, I'm afraid.
Do you know what software, do you know what computer was the software?
Yes, chemical engineering has the software, but if you go through RAS, do you use RAS or not? HIC is in RAS. So, if you go here and you write RISNCL, then you're able to log in remotely from any computer, and then you just click your the same thing that you use to log in any of the computers here, and then you go here, engineering software. Oh, sorry. So, well, now I've logged in, but so you go here and you go through engineering software and you click Aspen HISIS.
Do we have it for our marine school?
Yes, you should have the RAS. If you go inside RAS, you should have it.
No, not all software.
Yeah, we don't have.
I remember.
So you don't have HISIS? Check it and let me know.
Oh, we don't have it. I already checked it.
You have it?
Yeah.
Well, I think there are 3 programs in here, and
We'll check.
yes, yes. So you should be able to install it in there, and then now I'm going to in Blackboard. You already have all the information on HISIS. A lot of outputs, a little bit more information on HISIS. So we're going to have some sessions on HISIS as well, but I think that you need to as well start looking at the software and start. Who has used HISIS before? Can you raise your hand?
I use another one. Check that.
Stuff available across.
You have it available? Okay. So yes, it's a nice software tool. So. Well, I don't know what's happened right now, but I think I need to register, or well, I don't know. I'll just leave it like that, but you'll be able to access it. Okay. So that's it for now. So I'll see you next week. Please do the tutorials and and then you should be fine.
You ask the solution for that.
Yes, so we'll go to that.
Sometimes students, he wants to do like a solution actually. What if he will send you the solution you were saying about the fee?
Yeah, the demonstrating fee. I'm inquiring about this with the school office. So,
Excuse me, extra handouts.
yes, I have to check it with the school office first.
Yeah, I sent the way.
Okay,
He will solve
cool.
part-time. He wants. I mean, I said to him to solve because he has the time.
Cool.
Part-time, but I think he finished this model last year.
Ah, right. I need to check it because he's not a student anymore. Is he a student? Oh, okay. Let me check it. Okay, let me check it as well because I told your colleague as well to help me out, so I'll have to check it. Can you send me, please, his name and details because I cannot guarantee that.
I don't know. You were explaining something about question 16,
Yes.
but I got the answer without using the method. So I don't know. Maybe something is wrong or something. Maybe I was wrong, but I got the answer correctly without using. Sorry.
Without using any method?
Without using all these the adiabatic and isothermal.
So how did you do it?
Okay, these are the parameters. I got the area, I got the roughness. Use the roughness to get my friction factor.
And then
I used this.
the ideal gas.
Yeah, I did gas. I used it to get the density. And the inlet. Then I got the velocity. I got the unit number. I calculated this. I got my friction factor. I calculated this. So this is my equation. There was no elevation at the inlet. There was no elevation. So then I neglected the kinetic, the v square over 2 Yeah. Then lost to fittings. 6 standard 90-degree bend valves. Gave me this. I got this. Added it together with this other part.
Okay.
And I have the pressure at the outlet given. I have this. That's all. I got it.
So yes, it might seem that it's the same way to obtain it because in here we're also assuming an ideal gas law.
Yeah.
So
So you don't really need to use all this.
to this that approximation to do it. So I think that perhaps it's the same way you did it. To obtain it. So you obtain the same value as in here.
Not perfectly the same.
Yeah, it's not the same, but very close. Yeah. Yeah, so instead of using the equation, you have used the other one. So I'll compare it anyway to the other one and see that you get that. But I cannot see, I mean, it's just the same thing, approximation of the ideal gas law
Yeah.
through the system. So let me, you gave me your name last time,
Yeah,
isn't it?
I did.
So
I've not finished. I'm still having issues with the last set of questions 17, 18, 19, 20.
but this is viewpoint, no? We haven't looked at the lectures.
Oh, the 18, 19, 20, right? Oh, okay, so I was really.
Yeah, so
cracking my head.
no. And these ones you should be able to solve them later on.
Oh, right.
But I'll check. I haven't been able to check with the school office, but I'll send your details and check.
Okay, thank you.
Okay. I'll see you next week.
Excuse me, how do we have the negative
Okay, the
sign
mass balance.
for when we consider the balance? How could it be negative?
So that's for compressible flow. G over dx. All of them are negative.
Yeah.
In this
When we
case.
say balance, we it's a positive term.
The changes in density over dx, so the density will be I will have to check it. So let me check it and I'll let
So I
you
think
know.
part of this was in the previous handout before we got to this. I think there was some brief explanation. I was
It's just because of a mathematical thing, I think.
mathematical expressions.
Yes, but I'll check it and I'll let you know. Yes,
Thank you.
On the ICs, the assignment, do we need to draw the flow diagram again? In the ICs
What do you mean,
for the assignment, the flow diagram that we have in the.
No, you don't need to draw.
Don't need to.
No,
Just solve
you need
the
to,
values.
but actually you'll need to perhaps define each one of the flows, because if you're going to give for each one of the flows the values,
Temperature
then you'll need
values.
to define each one of the flows. Yeah?
They're training all the time at the same team. Complain. But you know you need to or they might update us. Draw my model. Our team was actually good to train for 4, 5, 6 times. I can't allow. Okay. You see it? I don't know if I saw the video. No. Diaz. Yeah, he was a good player, yeah.
And then he went for he was good, kind of good deal, but very inside.
They're all rich guys. They all they're rich. Yeah, oh my god, that's so fun. How about ASEM? The second girl, the third girl. One of them was ASEM. Yeah, no, another one.
So you stay there one day?
One night. This guy, yeah? This guy is. Oh, you choose a very expensive restaurant, I think. I think. Yeah.
Check later.
One off. Okay, let's high-five. How?
Bro. So where you go?
Library. Every day is counted. So where did you stay then?
Why?
Where? In Manchester.